Hi guys, our next lecture we're going to take a look at some types of solutions and what types of terms and math is used in expressing concentrations. So the first part is a little bit of the terminology. So a suspension, this is something from back in physical science, right? Suspension is a heterogeneous mixture of two or more substances. Remember, the big thing about a suspension, the particles do not dissolve. They stay suspended for a period of time, and then they either float to the top or they sink to the bottom. You can make a suspension by kind of stirring a mixture of sand and water. After you stop stirring, the sand's going to sink to the bottom. Milk is actually an example of a mechanical mixture. It will separate on its own if you leave it in your fridge long enough. If you keep paint for a while in a can, the chemicals and the colors will separate over time. So in a suspension, the thing to remember is that the concentrations are different at different locations within the sample. Solutions or homogeneous mixtures will not separate. A solution will never separate as long as the pressure and the temperature remain constant. If you dissolve sugar in water at 25 degrees Celsius and keep it at 25 degrees Celsius, the sugar will never leave the water. The difference between the heterogeneous mixture in our homogeneous mixture or our solution, the concentration of each type of substance, sugar and water, let's say, is constant at every location within the solution. There's not going to be a higher concentration of sugar near the bottom of the glass or something like that. As the water evaporates, like during distillation or something, particles will actually fall out of the solution. So we'll talk a little bit about chromatography later in this lecture. Solvent's going to be the substance that's more plentiful, often the thing that is doing the dissolving, and the solute, the substance that is less plentiful. So when sugar dissolves in water, sugar is the solute and water is the solvent. A saturated solution, and the rate at which particles dissolve is equal to the rate at which particles fall out of solution. This has been tested. To test it, you make a standard solution with non-radioactive isotopes, and then you add the same compound containing radioactive isotopes to the solution. So at first, all the radioactive isotopes sink to the bottom, but over time, they end up evenly distributed throughout the solution. And they can measure the rate at which alpha, beta, and gamma particles come out of the solution. The concentration remains the same if the temperature remains the same. If some water evaporates, then more solid will precipitate, and the concentration will remain the same there. The new concentration will remain the same if the temperature remains the same. We'll look at some types of solutions. A liquid-liquid solution. Here we have methanol. All alcohols have a hydrocarbon chain with an OH group, and their names all end in OL. There's our OH group. That little OH group will now give our alcohols the ability to dissolve in water because it can form hydrogen bonds. Methanol will dissolve in water due to the strong hydrogen bonds that they form with each other. They are miscible in all proportions. This means you can dissolve a little bit of water in a lot of methanol or a little methanol in a lot of water. The two will always dissolve one another. That's not true for something like salt and water, but it is true for alcohols. So a liquid-liquid solution. Here, water and hexanol will form a solution, but they are not miscible. They are not soluble at all proportions. So they do form hydrogen bonds with one another, but this really long hydrocarbon chain limits its solubility in polar solvents. So water molecules have a greater attraction then for one another than they do for the nonpolar hydrocarbon chain, which can only offer weak dipole, induced dipole, London dispersion forces. So alcohols with more than 3 carbon atoms in a chain are not miscible in water. That nonpolar becomes too big. So the solubility of alcohols in water decreases drastically as subsequent carbons are added. And alcohols with more than 6 carbons are not soluble in water. Some liquids are miscible in one another and some are not. So a liquid may be soluble but not miscible in a certain liquid, and completely miscible in another liquid. It's going to depend on the types and the relative strength of the intermolecular forces that exist between the species. Here, 1-hexanol exhibits strong dispersion forces due to its long carbon chain. So it's highly soluble in other nonpolar liquids. Solid liquid solutions, many ionic compounds dissolve in polar solvents, so that's our ion-dipole interaction. Polar solids, like glucose, dissolve in polar solvents because of dipole-dipole or hydrogen bonds. And then nonpolar solids, like mothballs, dissolve in nonpolar solvents because of London dispersion forces. Gas-liquid solutions, when carbon dioxide dissolves in water, it actually forms carbonic acid. So this creates a solution of carbonic acid and water. And so for this reason, water that is open to the atmosphere is slightly acidic. And carbonated water is even more acidic. And in some tropical countries, if you travel, it actually may be safer to drink carbonated water because the acidity will actually kill more bacteria. And if your water's carbonated, you'll know that it didn't come from the tap. Oxygen dissolves in water, so it forms a solution of O2 and H2O. And we saw when we did intermolecular forces, you have dipole-induced dipole forces. That's what allows oxygen to dissolve in water. Any water that's open to the atmosphere contains all the gases that are above it, like oxygen and carbon dioxide and nitrogen. Gas solutions, air is a great example of that. Air is composed of about 79% nitrogen. So nitrogen is the solvent in the gaseous solution that surrounds you right now. So every other gas in the solution, if air is a solute. So kind of a great example of a gas solution. Gas-solid solutions are interesting. Hydrogen gas can occupy the spaces between metal. There's always some hydrogen gas in oil and natural gas, and it can become interstitially kind of stuck in there, in here, between iron atoms in steel pipelines, and because of that, it's going to make the steel brittle at low temperatures because hydrogen will actually push the iron atoms apart. So to prevent leaks in pipelines, they actually remove as much of the hydrogen gas as possible out before they send the gas and oil down a pipeline. Solid solutions are formed by melting. We've seen examples of interstitial alloys. This is steel. Carbon's going to fill some of the spaces between iron atoms. Some properties of steel. We came in contact with these before. Pure iron is relatively soft, ductile, and malleable because it lacks directional bonds. but carbon forms strong directional bonds with the iron atoms. And this is going to make steel much stronger than iron. So by filling those interstitial spaces, the alloy becomes less malleable or more rigid. So the more carbon you add, the stronger the steel becomes. Here's brass, a substitutional alloy. And we have copper and zinc. Copper is actually the solvent because there's more of it. Zinc is the solute. And in an substitutional alloy, the mixing metals, or the metals have to have a similar atomic radii. It can produce, mixing metals and the proportions that they're mixed in can actually produce different properties. It can change the strength to weight ratio. This is super important when they make bicycles and stuff. So we express concentration. Two methods that we're going to look at are molarity, which you've seen before in honors chemistry, moles per liter of solution. Molarity can change with temperature. And mole fraction. Mole fractions do not change with temperature, so make a note of that, okay? Molarity can change with temperature. Mole fractions do not change with temperature. So molarity, moles per liter. A 3.75 gram sample of sodium chloride is dissolved in water. The total volume of the solution is 768 milliliters, which I'm going to right now make 0.768 liters. Okay, what is the molarity of the solution? Well, molarity is moles per liter, so we just need to get our moles of sodium chloride and then put it over our volume. And so we can take our sodium chloride, convert it to moles, and then take our moles of sodium chloride in our 0.768 liters of solution. A couple important things to note. Make sure you convert to liters, and then we'll pay attention to our significant figures. We have 3 significant figures here, 3 significant figures here. You'll see our answer has 3 significant figures. You can rearrange the math. How many milliliters of 0.245 molar sodium hydroxide are needed to deliver 1.7 moles of sodium hydroxide? So a little bit of math here. You'll start with your 1.75 moles, and then molarity is moles per liter. So we have to cancel out our moles, so we can actually put the 0.245 moles at the bottom to cancel out our units here in 1 liter of solution. So we can write it either way and use it as a conversion factor in this problem. And then we were asked about milliliters, so we have to convert our liters to milliliters. 3 significant figures because of the data that we've been given. And so 7140 milliliters of a 245 molar sodium hydroxide will deliver 1.75 moles of sodium hydroxide. Suppose you need to prepare 100 milliliters of 1.00 molar sodium or ammonia using 1.25 molar ammonia distilled water and 100 milliliter graduated cylinder. How would you do that? Now, I like to use M1V1 equals M2V2. So I need to prepare 100 milliliters, and as long as I have the volume in the same units, I can keep it as milliliters. So I need to prepare, that's going to be my final 100.0 milliliters of 1.00 molar ammonia. I'm going to use 1.25 molar ammonia. So let me grab my calculator, and I can take 100 and divide it by 1.25. So I'm going to take I need 80 milliliters of my 1.25 molar sodium or ammonia, which is kind of what happens here. And I brought this up to show you the procedure. You would pour 80 milliliters of the 1.25 molar sodium hydroxide into the graduated cylinder, and you would add distilled water until you have 100 milliliters of solution. So make a note of this procedure in case you're asked to make a solution. Now, I like to make my solutions in a volumetric flask, and I'll show you that in class. Remind me to do that because I believe you get a more accurate kind of measurement. Mole fraction. You will find the mole fraction of potassium hydroxide and the mole fraction of water in a solution that is prepared by dissolving 1.5 moles of potassium hydroxide in 1 kilogram of water. First, I would probably convert that kilograms to grams. And then from the grams, you can find the moles of water. So you'll find the moles of water. So first you'll do the kilograms to grams, and then 1 mole of water is 18.02 grams. So we have 56 moles of water and 1.5 moles of potassium hydroxide. So we have a total of 57.5 moles in the solution once we mix them together, and so we can find the mole fraction. The mole fraction of the potassium hydroxide is the 1.5 moles of potassium hydroxide over the total. So the mole fraction of potassium hydroxide is 0.026, and the 2 mole fractions together will add up to 1. You can always check your work again though. So if we went back, what did we have? 56 moles of water. Okay, we can do 56 moles of water over the 57.5, and we can double check our math. If I put the right numbers in my calculator. So again, I get 0.974. So working with mole fraction. Now you can pause on this slide. Scan the QR code, let me know that you watched the video, and if you have any questions, let me know. Go back and look at the assignment, and as always, if you have any questions, just let me know. Thanks, guys.